Today's technical corner. If I said to you I could improve material removal rates, reduce your cycle time and reduce the number of operations, you'd be interested. Well, today we're joined by Matt Kavanagh from MSC Industrial Supplies. So first of all, people who don't know you, Matt, give us a quick, about yourself and about the company very briefly.
Yeah, for sure. Thanks, Colin. So Matthew Kavanagh, Head of Engineering at MSC, been an engineer for 20 years or more. MSC is a industrial supplier of metalworking MRO PPE to nationally over the UK with strong expertise into metalworking.
Okay, so essentially you could provide thousands of products, but it's not just a product, you're providing that technical expertise as well.
For sure, for sure.
And it's not just you, is it? There's a big team.
It's not just me, no, there's 20 engineers.
Right, okay, we'll come to that later though. So today though, we're going to find out what I said earlier, improving material removal rates, reducing cycle times as examples. We're going to be doing that with the MillMax product, but first of all, we're going to do a very quick overview of the product on this video just here.
Great.
We don't make milling machines, milling tools, or milling software. We just make them all mill better. Here's how. Unlike other machining operations where the cutting edge never leaves the workpiece, milling has hundreds of individual tooth impacts per second, generating forces that cause deflection and vibrations. Like this 75-pound anvil, every tool is flexible and vibrates at its own unique frequency. Why is this important? The tool point deflects and rebounds at a frequency determined by the flexibility of the tool holder and spindle. You also have a tool impact frequency determined by the number of teeth and spindle speed. You have to get the timing of these two frequencies just right. If you do, each tooth is cutting equally, so tool life, productivity and quality are maximised. If the timing is off, a tooth arrives too early, undercutting and throwing off the next tooth. If it arrives too late, exceeding the programmed chip thickness, it leads to premature tool failure, poor surface finishes and possibly scrap. This timing mismatch keeps getting worse and leads to chatter. Without knowing the tool's frequency, the common response to chatter is to slow down the spindle speed, vastly underutilising the capabilities of your machine and tooling. As we said earlier, every different tool, tool holder, machine combination vibrates at its own unique frequency. The challenge is that there are millions of potential combinations. MSC MillMax measures the frequency of each tool and instantly generates a dashboard that calculates the precise, stable speed and feed rate, width and depth of cut for maximum performance. It also determines the best speeds for surface finish and accuracy. This patented and proven technology is in use in the world's largest manufacturers and is available exclusively from MSC's engineering team. Contact MSC today.
Wow, Matt, it's only a 2-minute video, but that is absolutely amazing. But I want to put you to the test. Have you actually got a real life example for us?
Yeah, for sure. So we took this software over to a supplier, manufacturer of tooling and supplier. So when we went there, they had a piece of... I'm
going to stop you there. Let's actually see the video first, shall we?
Okay, yeah, let's do that.
So Matt, talk me through what's gone on here then, please.
Yeah, so as I say, we went on site to a supplier. They helped us out with the material and the tool setup. We went in, we put all the data into the software, tapped the test, and we got over and above beyond wherever they'd managed their optimum performance of there. Bearing in mind this supplier, they use their tools, they go and do trial and tested, they have internal conversations, they work with their customers, and throughout a 2-year period the supplier got the optimized data of what they thought. Within 15 minutes we actually gave them over and above what they thought that was the optimum data, and we'd almost doubled their output of their optimum performance.
So you've walked out with a big smile. They've walked out
for sure. Yeah,
brilliant.
I mean, it was all over internally on their internal work.
Absolutely fantastic story there. So I want to take a step back then, and the start of this sort of process is sort of the bane of engineers, and that's your chatter. We've got a great example of a video from after this video. We'll go into that. Okay, tell me what's gone on here then, please, Matt.
So yeah, you can hear the chatter on there audibly. What's actually happening is, crudely, the actual tool's wobbling, so it's got resonance in there, and you can hear that chatter and that movement as it's machining.
And every setup has its own resonance, its own thumbprint, essentially.
For sure.
Okay, but we'll come to that in a little while. So that's pre-MillMax, post-MillMax. I think this tells the whole story. So now, could you hear that? Absolutely, you couldn't hear it. I mean, that was like a knife through butter. It really was. So what's happened here though?
So what we've done is we've actually found, it's kind of like I always refer it back down to like a hearing aid. It's about that person's frequency that they have, and it's unique to them. Same characteristics here. It's the right frequency, or the stable frequency, regarding the characteristics of the actual setup.
Okay, well that ties in perfectly with what I want to cover off next, which is the actual setup. So you've got here the mill. Obviously, we haven't got a machine and a spindle, but you've got the tool holder. Talk me through what's going to go on and how it ties in with the resonance.
Yeah, for sure. So here we've got, let's say, a machine on, I don't know, said concrete, or it might be on anti-vibration pads. We've got the build-up of the linear rails. We've got the spindle, and all of these elements offer a certain resonance. When you then add the complications of the actual tool and the tool holder and the tool assembly, or any adapters, you've then building up the frequency levels a hell of a lot more than what it would be previously. So it's about then finding that unique stability, or eliminating that resonance, to be able to understand, pinpoint where you should be machining.
Okay.
Using
eliminating the resonance or identifying the resonance?
I think both, actually. Okay. So we'll see that on the dashboard.
Okay, so you've got, essentially every single setup is unique pretty much. So you've got that setup, you've got chatter occurring. I've contacted yourself at MSC, said I need you guys to come out and get the MillMax and do the tap test. So what happens?
So yeah, before we even come on site, what we'll do is we'll have a look at some characteristics of your machine setup. So we'll want to know the machine itself. A picture tells 1,000 words of a tool setup, so that would be great. What material you're machining, what's the strategy you're using, so your depths, your speeds and feet, your radial engagement and so forth. And then from that we can compile all of that data into the software, and then physically we just need to come on site and do a quick tap test on the machine.
And you'll get this stability load. But take a step back. In very basic terms, you've got it here, the hammer accelerometer though, it's not just a hammer. So what do you do? Yeah,
so we have, essentially, we've got the tool holder of the tool, which will be static into the machine.
So not turning,
it's not rotating at this point. We have a 3D vibration sensor with some jelly that are just
very technical.
Some petroleum jelly that sticks onto the flute of the tool. That will stay there throughout the whole duration of the tap test.
Okay.
Obviously, the spindle isn't rotating still at this through the duration of the tap. We then, whilst that 3D vibration is stuck onto the tool, we have a hammer which we will tap onto the tool.
No, it's not a hammer though, is it?
We'll call it an accelerometer.
Yeah, I've got to get that right.
So we will tap the tool, and then once we tap that, the actual software will tell us whether it's doing a double tap, you've tapped too hard, you've tapped too soft. So it is very sensitive to make sure that you get the right information back into the software.
Okay, so you're doing all this setup. I mean, you've got the data in advance, you're doing all this setup. I'm a machine shop, I need to be making components, making money. My machine shop's going to be down for the day.
So no, completely incorrect there, actually, Colin. What we do, because we're doing all that back work, and because we're taking all that data, we'll input that into the software already.
Right.
So we'll literally use that vibration sensor, put it onto the tool, onto a static tool, tap the actual tool itself. There's a number of taps we do in one direction on the axis. We turn it around, do another same amount of taps in the other axis in Y and X. And then once we've done that, we've got all the data, we can come away, analyse it. You could even carry on with your production, and then we can give the optimised data after, so it will eliminate in the downtime.
Okay, so roughly, what, 15 minutes?
15 minutes, yeah, for sure.
So that's brilliant. Now, that's 15 minutes. What before, though, I was doing it, how would I do it? How would I sort of remove the chatter? And
Yeah, so chatter's been apparent for, God, centuries, and it's been the bane of an engineer's kind of existence. So what tends to happen is, one, I suppose the engineer, when they first come to use the data, is they'll look at book data and choose the middle ground, and hopefully they get stability straight away, and they'll try and optimise on the feed rate of the actual machine, or the spindle speed, shall I say, on the machine. So that's increasing the speed rate, the speed of the tool. But in other instances, they could put that data in and they hear chatter instantly. And the first thing to do is, hey, back it off, don't go so fast, and you get that stability.
Okay, so that's that's really down to experience. So that's going to, that could take hours, weeks, months to get what you think is the correct.
Yeah. So there are instances where you get stability, and maybe you're in a bit of a rat race where you've got loads of jobs coming through. You're trying to do some continuous improvement. You've got jobs not kind of being successful because you haven't got that efficiency there, and you're trying to run around. But if you've got some stability, let it do and let's carry on. You might come back to it another time, and it could take, I don't know, hours, sometimes weeks or months to really perfect. And again, as you quite rightly says, 15 minutes and we've got the optimum. Okay,
so you've got the data for that setup, for that machine, the tool holder, the tooling. You've done your tap, then get the stability load, which will talk us through what this actually is.
Yeah, so the white parts are in there, are the actual, the depth of the tool that's engaging into the material.
Okay. Yep.
So in between these peaks and troughs, between the red and the white parts that you can see here, you can see at the bottom part the actual spindle RPM.
Yep.
And then, so as I just said, on the other axis, you can see the depth of cut.
So depth of cut here, spindle speed there, and that's obviously individual to each machine. So it could be 12,000, 15.
Yeah, it's unique whatever RPM, max RPM the machine's got. And then within the white areas are the stability parts.
Yep.
And then you've got this thick red line that comes around there, which is a warning, so unstable, a warning, shall I say.
Yep.
And then the crosshatch, unstable, chatter, avoid like plague. Yeah.
Okay, so red, amber, green, it's nice and simple.
Yeah.
I want to be machining in the white bit, but the most optimum white bit, essentially. Okay,
for sure.
So the engineers, this data's great, but what they want to see, something more usable that they could tie in. So that ties in nicely with our next slide, which is the dashboard. So that stability load, that you've got your data, you've done your tap test, you've got stability load, moves into that.
Yeah, so on the right hand side of the screen here, we can actually see what the customer would see then, and we can actually give a sample to the customer of what we've tapped as well. So again, just like what we talked about from the stability load, we've got the green, amber traffic light system.
Yep.
Within there, you can actually then look at the different defining moments at this data, which is the depth of cut and the width of cut, and where them stability parts is unique to that material engagement.
Okay, I'm going to stop you there though, because what we alluded to earlier, you tried and testing, you're changing the speed. So before, an engineer might have gone up to 7,000 and then maybe backed off a bit, but you're telling me that they actually could have been machining up at 12, 14,000 potentially to get that.
Yeah, for sure. So there are cases where you go, and in this case, yes, at six.
It's an interactive, so we'll come to that in a moment. But yeah.
So within that instance, you might go at 6,000 RPM. You might increase the feed and hear chatter, and you think, I don't want to go any further.
So,
come straight back where the stability is. Time to break the machine. I've got loads of operators looking at me as well, and then little did they know, maybe 1,000, 2,000, 2,500 RPM. There was a stability area that you wouldn't get to, not unless you're really trying to define.
Okay, so if I can increase that, what results will I get? Material removal rate.
Yeah, so you're going to increase material removal rate for sure. You're going to decrease the cost per part. You're going to be looking at prolonging the actual tool life itself, and most important, not only are you looking at after the actual tool itself to get the maximum out of the procured item, but you're looking after the capital investment of the machine, because don't forget, all of them vibrations are emitted directly into the spindle as well. So the spindle bearings, the lifetime of that bearings are going to disintegrate, and you really want to capitalize on the effectiveness of your machine tool.
you've got to have this, this solution. It really sounds like you have to do that. So taking a step back, then we've got the interactive software, which we're going to get back up on the screen now, because it is interactive. So you've got your radial, your radial and your axial cuts here. You can move it around. Well, you talk me through it, please.
Yeah, sure. So there's loads of different ways to explain it. So we've got the AP and AE, what engineers typically all know and use, but we've got radial depth of cut and the width of cut, which is the AP and the AE. So first of all, on the actual dashboard, it's kind of like a rev counter on your car.
Right.
So it tells you the maximum RPM on that spindle.
So 12,000 on a Herco machine in this instance.
Yeah, and if it was a Herco with 15,000, then it would be 15,000
Any
maximum
machine?
RPM. Any milling machine.
Yep.
So what we also put in there is actually it's governed by the actual kilowatts as well. So we actually put the actual torque load into the software itself. Once we've got all the parameters, we've got the material as well.
Okay. So material group down here.
Yeah, for sure. So whether that's P1, P2, Inconel titanium, austenitic stainless,
Plastics.
plastics.
Composites?
Because the tool still vibrates. It's not so much the workpiece in that scenario, but because obviously you're looking at that material, it will give you the quadrants that will work with the material.
So you've got your sort of your set data there, and then you get to play around. I'll say play around with that. It's not very technical, but on this side,
essentially, yeah, it is. And I suppose this is the fun part for any engineer, because you're not only just looking at where the stability is, but you're actually trying to define what kind of strategy you look at and play with. So if you've got the crosshairs here, so the yellow part here is the actual engagement of where the tool's cutting the material.
Okay.
So you can get the crosshair and move it over to the far right, and you can see straight away that we've got a load of instabilities and chatter.
So here, essentially, a massive big depth of cut,
massive depth and radial.
Yeah. So you can't push it too hard. But if you're bringing it, say, down to here,
so if you bring it right the way down, then so you've got stabilities. But if you actually bring it still in the same quadrant, but bring the tool length all the way to the top.
Okay, yeah.
So you can see now, and actually if you move it towards the left-hand side to reduce that material, you can see now we're starting to get little parts of stability. And then you can start moving the length a little bit further down and carry on further down. And then you can see little parts of stability starting to open up. Okay. So you can really have a play with how you use the strategy.
Okay. And then you can use this here, but then you can type it in here as well.
You can actually define. So if you've got 12.356, you won't necessarily program in that way. So you'd try and round it up to make it a little bit more the data a little bit more stable.
So that'll be here, for example.
Yeah. So the depth of cut, you can go on there and change that to 18 mil or something for argument's sake.
And as if by magic, there you go.
And as if by magic. Yeah. And then the next one down for the width of cut. In fact, you can actually change on the right hand side where you've got percentage. You can change that to millimeters or the percentage engagement, which is great for trochoidal machining when you look at 10%, 15%, 12% engagement, whatever it may be. Okay.
So ultimately, you've got this. You've done your tap test. You've got this dashboard. You can change how you want to do your cuts and things like that. Then you're going to get, as we mentioned earlier, improved material removal rates, cycle times. But you can vary the way the application in terms of the strategy. So you can have longer tool life or better surface finish, or
so we've seen a video earlier when we talked about the dormer, and you could possibly see some of the imperfections on the material, and that's purely because what we want to try and do is have a look at, yes, you can actually run a tool stable but a really high metal removal rate. Yep. But when you want to start looking at the actual surface finish for, thin wall machining, you can actually utilize the software to actually look at the accuracy expectations and the surface finish. Wow. So when you see the dashboard again, at the bottom of the screen, you'll actually see where you can actually get surface finish.
So if we can just go back to the dashboard there.
Yeah. So if you look further on down, you can actually see now a graph there where we can actually see where the lower that structured line there, the better the surface finish.
Okay, so I'm thinking if you're going for a better surface finish, you can maybe remove other operations such as your grinding, polishing.
Depending on the actual machine itself. So this again, we talked about MSC's engineering capability. So this is great having the software and knowing where the stability is, but actually understanding what you can physically do on the machines and its capabilities is another thing in itself.
Okay, Matt, absolutely fantastic product, service, the MillMax and MSC, it really is. As we've been going along, I've been thinking of questions, and there's going to be loads more questions out there. So I'm hoping you'll get inundated, not too many, too tricky, but I think we alluded to it. This will be any setup, so machine, etc.
Yeah, so any tool from indexable, high-speed steel, carbide, cobalt, single point boring bar, live tooling on a lathe. So anything that's rotating, we can tap.
Okay, and I think we've covered this already, but just to reiterate, how long to actually do this?
15 minutes.
Right.
Purely because we're taking all of that data before we even get on the shop floor, and then analysing the data, the customer's back in production.
Okay. Now you said pretty much any type of tool. Any sizes?
Yeah, so obviously we're using the accelerometer to actually tap the tool. So I would say from anything from 8 mil up to 150 mil.
Right.
And then obviously 150 mil, what we do is we actually put a weight on the actual hammer, because we still need to try and get the resonance back through there. The accelerometer. Thank you very much. You should do our marketing.
Okay. That's it in a nutshell. So that's just a couple of questions. I want to speak more generically about, this is looking at that side of things, but in your machine shop, how's it going to affect your machine shop?
Yeah, I mean, it's quite a big question, that is, Colin, because you've got everything coming back from reshoring now. So people are wanting to try and take back the work. They've got the work that they've already got going on at the moment. They've got headcounts coming back from furlough as well, which is just some more added pressures. They've got to buy the material. They've got to buy all the production elements to it.
Yep.
Trying to add all that in and get efficiency out the shop door, the shop floor, to try and get the sales generated as quick as possible. What we need to try and do is get stability and certainty within our shop floor, and it's key to get the data right.
Yep.
As long as you've got the data right, and as long as you've got best practice, you can actually utilize, and MillMax, I mean, for sure, when you've got that optimized data, you can use that within your shop floor to make sure that you've got effectiveness throughout each operation.
Yeah, so make it in a nutshell, making far more efficient, really is.
Yeah, you can, it's making sure that you've got the metal removal right, the cost per part right, you're quoting more efficiently.
Yeah.
If you're quoting more efficiently, you can have a look at getting more retention from the customers that you've got. You can beat the competition. You can increase lifetime agreements with certain parts. Maybe you give a little bit of margin away to retain a little bit, but it's all about how you support the shop floor.
Yeah, and this does, hopefully coming to the end of a pandemic at the moment, but engineers have had that time. All right, they're still busy and they're getting busier, but from what we hear out in the market, but they've had time to take a step back and think about more efficiencies, and this ties in nicely with it. Yeah,
for sure. I think it's made us all kind of reflect, really, even just about boots on the floor. So we talk about from a sales point of view, it used to be, okay, we've got to be speaking to the customer, we've got to be amongst the production. But MSC takes a different stance. What we want to try and do is quantify all the data, understand what the outcomes are, how you want to redefine and reposition your business to make sure that we're actually supporting and helping the business.
Okay. And providing an unbiased solution as well.
Oh, for sure.
Yeah. Okay. Now, what sort of machine shops is this aimed at? Is it your one-offs, your bespoke parts, or your big production?
Yeah. So quite a lot of people that I've been speaking to really think that because you're tapping a specific tool, it would work really good in a production environment.
Yep.
Because that tool is always going to be set up, said ejection distance from the tool holder, and cutting in the same way. What we're looking at and what we're utilising it as is, if you've got the tooling set up in a specific way and you're machining a certain type of material, you should use that data to qualify and machine the material away in the same way to get continuity.
Yeah. Matt, thank you very much for your time. It's been a great insight into MSC and the MillMax. It really is absolutely brilliant. So if you've got any questions, I need to get in contact. Well, it's all over the website. You can't miss it. There you go.
It is.
Thank you very much. I hope you enjoyed the show.